What if your car didn't need fuel? What if it could suck energy straight from the ocean and run forever? You'd have a 100% efficient engine, which is something we've never built and never will. This is why. First of all, what is a heat engine? A heat engine is a device that turns heat into useful motion, so work. For example, it's very easy to create heat just by rubbing your hands. But how do you turn this heat into something that actually does stuff? You'll see examples of this, like car engines exploding gasoline to push pistons, which move your car, or a steam engine that boils water to drive a turbine. But here's the key: heat doesn't magically become work. It must flow from something hot to something cold, and then only then can we extract motion from it. That's the core idea behind all engines and is rooted in the second law of thermodynamics. Let's say you have a block of hot iron at 600 degrees Celsius, and you have another one at 20 degrees Celsius. If you connect them, then eventually the heat will flow from hot to cold naturally, right? Thermal equilibrium. And what a heat engine does is it captures this flow while it flows across from hot to cold, and it converts some of it into useful work before the temperatures of the two things equalize. Because remember, that's how heat works. You don't have heat if the temperature is the same. Heat is the transfer of energy between something hot and something cold. I'll show you a diagram that represents this. Let's build it. Up here is our source of high temperature, so we'll call it temperature H for high. And then we got heat flowing like this. But at here it splits off. Here, down here, is our low temperature area, like our iron block here. This is where the heat flows. This is QH, which is heat absorbed from the hot source that now is flowing. And we'll represent this portion as QL, which is the heat that's dumped and wasted into the cold sink. This part that splits off we'll label W. This is the work that our engine extracts. And this is what does stuff. This is the difference. This here is the idea of a heat engine. So, by the conservation of energy, the heat that's flowing from the hot source, QH, is equal to the amount that goes and gets wasted into the cold area, plus the portion of it that gets directed into actual work. We can isolate work here and we get this equation. Work equals the flow from the hot minus the flow that goes into the cold and doesn't turn into work. This, of course, is all on the free cheat sheet in the description. But we also have to talk about engine efficiency. So like at the start of the video how I said we'll never build a 100% efficient engine, here's why. Efficiency, first of all, let's define it. It is the useful output that we get divided by the energy input that we put into the system to get this output. And this is work because that's the useful output divided by the energy input that turns into work, which is the flow from the hot thing. If we substitute in that little equation that we found for work earlier, we substitute it into the top, we get this. Efficiency is equal to work, which is QH minus QL divided by QH. Because of the way you can rearrange fractions with your excellent math skills, you can also write this as 1 minus QL divided by QH for efficiency. This means that the less waste heat that you dump out, the better your engine. Because if this number is smaller, then the total overall value is going to stay bigger. But why can't this efficiency value be 100%? Why can't this ratio here be 0? Let's say you try to dump no heat into the cold sink. So if you remember our system, we have the heat, we have the way it flows, so like that, and we have the cold area where all the wasted energy goes. Let's say you try to dump 0 of your heat input into here, so all of it gets directed into real work. That would mean the flow toward the cold sink, and we call it a cold sink because that's where all the cold's going. The flow toward that has to be 0 for your efficiency to equal 1 or 100%, which means that 0 of your heat input flowing in from your hot source is lost. None of it's lost. All of the heat becomes work, and you've now violated the second law of thermodynamics. You're getting free energy forever. That's why every single engine has to dump some of your heat out into the environment, or whatever this cold thing is. Even your car guess how much energy it dumps out? So from its heat input energy, it dumps out 70 to 80% of your input. So not a lot of it actually turns into work. It's impossible to make a 100% fully efficient engine. It violates the second law of thermodynamics. In 1824, this dude named Carnot proposed a thought experiment. What if we built a perfect engine? And he imagined this ideal engine as a machine that turns heat into work, with zero friction and no energy lost. What would its maximum possible efficiency value be? And he realized something strange. Even the most flawless engine can't turn all your heat into work, since heat has to flow from something hot to something cold, and some of that energy must leak out to the cold side before you can extract it all. That leakage is not a flaw, and he built a thought cycle, a perfect loop of processes that are all reversible. So in theory, you could rewind all of these backwards. I'm not going to go into them, but I will name them for you. Isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. These are all reversible. You imagine you could go from one process to the other, so isothermal expansion, and he calculated how efficient this cycle of reversible processes could be, assuming no friction, no leaks, no imperfections. The efficiency of the Carnot engine is 1 minus the temperature of the cold bit divided by the temperature of the hot bit, where the heat's coming from. And it's in Kelvin, and this is the ratio. What this means is that no real engine can beat Carnot. This is the upper ceiling for efficiency. Real engines are always worse because there's real life stuff going on like friction, turbulence. And if it's impossible to have your heat when the temperatures are the same, then your efficiency simply depends on the temperature gap. So engines are hot at the top, but on the bottom they're as cold as possible, which is where the cooling happens. The Carnot ideal engine is the roof of engine efficiency. Here's a real engine example that we're going to go through. Let's say your car engine produces 30,000 joules of work every single second, and it has an efficiency of 25%. How much energy is going into your engine and how much energy is wasted before it runs your car? Take a look at the formula, which by the way is on the free cheat sheet in the description. You can find the flow from the hot, so your input. It's work divided by efficiency. We got this from the efficiency formula, but we just rearranged it, because that's what we're looking for, right? We're looking for how much energy is going in and how much is wasted. The work it's doing is 30,000, and the efficiency is 25% or 0.25. This is 120,000 joules of input. So that's how much energy you're putting in to get this result. So what this number tells us is that your car does this amount of work, 30,000 joules every second, and the fuel it eats up is worth 120,000 joules. Where does the rest go? It's dumped into the air and it's wasted, which is 90,000 joules. That's like paying $4 and you get $1 of value. The rest is smoke, heat, and sound. But before we move on to the next part of the video, which is about your fridge and your air cons, real life stuff, here's some final insights. You cannot have a 100% efficient heat engine, and every engine must exhaust heat to keep it running. The ceiling of engine efficiency is the Carnot engine, and it only depends on temperatures, not the engine type. So this next part of the video is about real stuff like your fridge, air conditioners, and heat pumps. Your fridge doesn't just make things cold. It's a backwards heat engine because heat normally flows from hot to cold. But your fridge reverses that. So the difference between your fridge and a heat engine takes in heat and it produces work. A fridge spends work to pull heat out of a cold space and dump it onto a warmer one. This is against the natural flow of heat. This is why they all require energy input, because we're forcing something to happen here. So here's how it's represented in the diagram. And it's going to be similar to our heat engine diagram. Here's the heat reservoir, you could say, the hot area where we're dumping our heat into. And this is where the cold is coming from, the cold area, because heat flows from hot to cold. Our fridge is here, and the path that our stuff follows. We have work going in, and we also have stuff going from the cold place to the warm place. So the flow of the cold is going up toward the hot this time. The flow of the hot is the combination of this flow of cold and the flow of our work. And this work input is usually something like an electric motor that compresses gas. And of course, the energy conservation equation for this is flow of the hot equals this plus this. So QL plus W. How about efficiency? How efficient are fridges? They're backwards heat engines, so they don't have an efficiency. We use something different. It's called the coefficient of performance. And this is shortened to COP. So the coefficient of performance, or COP, is given by a similar thing to the efficiency formula, but it's upside down. It's the flow coming from the cold into the hot divided by the work. And work, we can find a different way to express it by isolating it here in this equation, which is QH minus QL. So we can plug that in for a final coefficient of performance equation of this. It's like the normal heat engine efficiency, but upside down. What this number means is a bigger coefficient of performance means better cooling per watt of energy. So it's more cold, so a more efficient fridge has better cooling for the same input of energy. Here's the difference between air conditioners and heat pumps. An air conditioner, what it does, we'll write AC, it pulls heat out of a room and it dumps it outside into the world. And I'm not sure if you know this already. In science, of course, it's impossible to make something cold. You don't make things cold. Cold is simply the absence of heat. You take heat out of something to make it cold. You don't add cold. It's not a thing. It's like how you can't add dark into a room. You take the light out. You turn the lights off to make it dark. It's simply the absence. So an air conditioner pulls heat out of the room and dumps it outside. A heat pump, so like a heater for your bedroom. Oh, I just deleted our room, but a heat pump pulls heat into your room from the cold outside world. Coefficient of performance for the heat pump is the flow from the hot divided by the work. What this means is the amount of delivered warmth per unit of electric input. It's how warm you get for a specific amount of energy. And why this works at all is because heat does not want to flow from cold to hot. The second law of thermodynamics, remember? Because this violates nature unless you add energy. It doesn't naturally do this. You can naturally go from hot to cold. That's what heat likes to do. But you can't go from cold to hot naturally. We need to force it with adding work. So you can violate or bend the second law technically by paying an energy price. Let's go through an example problem. So you have a 750 gram fruit smoothie and you chuck it into your fridge. The smoothie starts at 0 degrees Celsius and the fridge has to freeze it solid without a temperature change, just a phase change. So remember, you can have a phase change without changing the temperature. Phase change meaning, for example, liquid to solid or solid to gas. This is what's happening here. We're going from a liquid smoothie to a frozen solid smoothie. How long does this process of freezing take if the fridge's coefficient of performance is 2.8 and it runs on a 150 watt motor? And remember, every single problem we use for this formula is in the free cheat sheet in the description. So what's our goal? First of all, we're trying to find time, but the fridge power is in watts and it has a coefficient of performance. So what we will do is one, we'll calculate the heat that gets removed from the smoothie for this phase change to occur, which is QL. Second, we'll use the coefficient of performance to find how much work the fridge must do to make this happen, so how much energy it's going to spend. And three, use the motor's power to find out the duration of this process, because obviously if it's more powerful, it's going to take a shorter amount of time. That's how we're going to link up to time. So it's only a phase change, liquid to solid. So the heat removed from the smoothie is, remember from latent heat, mass of your liquid multiplied by the latent heat of fusion. Because this type of phase change, ice to water, is a fusion one. This is 0.75, and we'll just say the smoothie is water, like easier, times 333,000. This gives us 249,750 joules of heat that's lost during this process. Step one is done. Next, we have to find the amount of work done by the fridge. We'll use the coefficient of performance because that formula has work in it, so we can simply rearrange for it. Let's use our excellent math skills and rearrange for work, and you get QL, which we'll substitute in now, 249 750 divided by coefficient of power, since we rearranged it. The coefficient of power will also sub in, which is 2.8. And the work done is roughly 89,200 joules. And here's what we've been building up to. So first we found the QL because it's involved in our work formula. Second, we found the work that's done. And now we can use our work value to find the amount of power to find time. Why do we need work to find time? Because there's a formula that involves time and work, and that is power. Power is the rate at which work is done. We can rearrange for time with our amazing algebra skills. Algebra is super important for physics. Find a way to excel at it. Physics becomes effortless. It's work, 89,000, divided by power. Power being 150 watts. So 89,200 divided by 150. You get roughly 595 seconds. So that's how long it takes, or about 10 minutes, to completely freeze the smoothie with a fridge with these specifications. And really, that's actually very fast to freeze something. So our fridge is pretty great. So that was it for heat engines, one of my favorite topics in thermodynamics.